video. Okay, let's see. What did I get graded this weekend? I can't remember. Something or other. I sent out something. Oh, I think it was the graded retakes on test 1, and I still have to do the graded retakes on, or grade the retakes on test 2. I'll be doing that later today somehow. And so then I have some things posted, some assignments on Canvas. There's a new sapling assignment and a new lab. And I think I've got just about everything posted I need to, except maybe last week's lectures. So I'll have to get those things posted. But otherwise, by the end of the day, I hope to have that test 2 retake graded, and then everything posted that we'll need up until our final, I think. Hopefully, except for some review stuff, but and then the daily lectures as well. So today we're starting a new area, and the new area is momentum, which is another one of those terms that has worked its way into common use, and most people have no clue what it means. So we'll learn about that today and how it might change. So we'll take off from there. Okay, share screen, visualizer, and we should be good to go. Okay, Isaac Newton actually started looking at momentum way back, fairly early in his studies of stuff. And Newton actually thought that momentum was energy, but we now know that it's something different. Energy has a different expression and a different formula, but momentum is going to be mass times velocity. Now, this is different from kinetic energy. Kinetic energy is 1/2 mv squared, and this is the speed that's squared with kinetic energy. And this is a scalar quantity. There's no direction to kinetic energy, and it can never be negative because you're squaring the speed. And even if you thought you had a negative speed or something going in the opposite direction, by the time you square it, it becomes positive. So this one's always positive, no direction. Momentum, a mass times a velocity. Velocity has direction in addition to magnitude. And so momentum is going to have direction as well. Now, I just forgot to check your textbook for the letter they use for momentum. I'm hoping it's the same one that I'm used to in my head, because, oh good, it is. All right. We're going to use the letter P for momentum. I'm trying to remember, oh, there was some book I used to be teaching something out of that used a different letter for it, and it drove me batty all quarter, but we'll use that. So it's just going to be MV, and I'm not putting arrows on it here, but it is the velocity that shows up over here. So pretty much all of the, or most of the problems we're going to solve are going to be one-dimensional. So I'll put a plus sign on something moving in the positive direction and a minus sign on something going in the negative direction. But we'll see how this happens to work out. Now, as a first example here, I want to look at Newton's second law and get something out of this. F net is going to equal MA, but I'm going to think about something taking place over, not instantaneously, but over a little bit of a unit of time. And the acceleration is going to equal the change in velocity divided by the change in time. And let's see, when I take that F net and multiply this mass times that change in velocity, well, this is going to equal the final velocity minus the initial velocity over the change in time. And so this MA is then going to equal M times final velocity minus initial velocity over delta T. And I'm going to distribute the M through here, and I'll get MV final minus MV initial, whoops, MV initial divided by delta T. Well, MV final is the final momentum. MV initial is the initial momentum of something that's being acted on. And so we could say that the net force is equal to delta P over delta T. And this is another way of writing Newton's second law. So I'll call this a new way, for us anyway. And anytime you've got a delta T on the bottom of something, you're talking about the rate at which something changes. So you could say that the net force that acts on something is the rate at which the momentum changes. Now, almost immediately, I'm going to multiply that delta T out from underneath here and say that F net times delta T is going to equal the change in momentum. Okay, when we were studying energy at first, we talked about something called the work kinetic energy theorem. And the work kinetic energy theorem, let's see, I'll write it down here. It said that the net work that acted on something was equal to its change in kinetic energy, which would be 1/2 mv final squared minus 1/2 mv initial squared. Now the net force, excuse me, not the net force, the net work that was done on something. I was getting ahead of myself. That's the net work is equal to the change in kinetic energy. The net work was equal to the net force times whatever displacement occurred. And that gives you that change in kinetic energy. Oops, minus 1/2 mv initial squared. I hope my notes are sloppy enough to confuse you. Let's see. Anyway, that's the net work. Okay, it's a force times a displacement. Here we've got a force times a change in time, and that'll equal a change in momentum. So there's something sort of analogous to the work kinetic energy theorem for momentum, although instead of calling this work, because it's not the same as work because it's got newtons times time, and so it's not going to be measured in joules, we'll call this thing impulse. And this is a formal definition of the use of the word impulse in physics. It's the net force times some change in time. Now, in general, the net force can be non-constant, like if you collide two things together, the force will start off not being very big and it'll get stronger and then it'll get weak toward the end of the collision. And so this can be kind of complicated, but we're going to kind of pretend it's relatively constant, that we can multiply it by a delta T and get the change in momentum. In general, you'd have to resort to techniques of calculus to be able to figure this out correctly, which we're not going to do. So don't worry about that. But anyway, that's the impulse. The impulse will change the momentum of something. Impulse that's given to an object. Okay, where did I put all my problems for today? That's just basically introducing momentum. Now, this is out of a higher level textbook than we use, but it's a fairly simple problem. You say a baseball has a mass of 0.145 kilograms. If the velocity of a pitched baseball has a magnitude of 45.0 meters per second, which is pretty darn fast, and the batted ball's velocity is 55 meters per second in the opposite direction, find the magnitude. Actually, before we do this, let's go ahead and calculate the impulses of a few things. So that we have some sense as to what kind of numbers we're talking about. Let's see. Let's imagine a 45.0 meter per second fastball. And this will be a baseball. And that other problem said that the mass of the baseball was 0.145 kilograms. So that's what we'll use for the mass of the baseball. Well, the MV in that case is going to be this 45, whoops, that's not the mass. We usually put it first. 0.145 kilograms times the 45.0 meters per second. And this particular combination of units, kilogram meters per second, we don't have any abbreviation for it. So we'll always just write it as kilogram meters per second, which is kind of nice, I guess. At least in this unit, you won't have a new unit to contend with. 0.145 times 45. So that has a momentum of 6.53 is as well as we can do here. And it'll just be kilogram meters per second. So we've got that. A walking person. Okay, we'll imagine that their speed is 1.3 meters per second, and they have a mass of, oh, I don't know, 70 kilograms. Okay, that'd be somebody who weighs about 154 pounds. So that would be that. Well, their momentum is going to be P equals mv, 1.3 times 70. Or about 91 kilogram meters per second. Whoops, that would be the 70 kilograms times 1.3 meters per second. Forgot to write it with the numbers tossed in first. Okay, so this is, I don't know, there's the baseball, 6.53. Here's 191. That's about, well, not quite 15 times as much, but anyway, it's more than 10 times as much for a walking person. A sprinting person, and this might not be a world record holder, but we'll just imagine here that maybe their mass is 75 kilograms and their speed might be 8.0 meters per second. Okay, their momentum is going to be, again, mv. So 75 kilograms times 8.0 meters per second. 560 plus 40, I think it's 600, probably. Yeah. 6.0 times 10 squared kilogram meters per second. Okay, so even though they're going quite a bit faster than the walking person, with momentum, it's just proportional to the speed. So you don't end up with speed squared like you did for kinetic energy. So it's not quite as much. Let's see, maybe one last example here. A 1,700 kilogram car at 70 miles per hour, or about 70 miles per hour, which is around, let's see, 31.3, well, let's just say 31 meters per second. And that's going to be close enough. It doesn't have to be exactly 70, but it'll give us a little bit of an idea of how much momentum it would have. So P equals mv, 1,700 kilograms times 31 meters per second. And it's going to be a bigger number, obviously. Yeah, 5.3 times 10 to the fourth, or about 53,000 kilogram meters per second. So by the time when you start increasing the speed to things like this, when you square this, you get 1,000. And so you would have had over 1,000,000 joules of kinetic energy, but momentum is just proportional to the magnitude of the speed, at least its magnitude is, and so not the square of it. So you don't end up getting these humongous amounts of momentum, although that's quite a bit. It's enough to pack a little bit of a wallop. So, but anyway, there's just a few calculations for this thing. Now, this very first problem I gave you deals with a change in momentum instead, or the first one that's on this sheet. And so let's take a look at what that's going to look like. And we'll imagine that the baseball here, just M, is headed in this direction. It's pitched at 45.0 meters per second. So going like that at the beginning, but then it's hit by the bat. And after that, it's headed in this direction at 55.0 meters per second. So okay, now the change in momentum, I'm going to choose to call the left the positive direction in this problem. And so that will be that. Now, the momentum that we have initially, since it's going in the negative direction, is going to be our mass, the, wherever it was, 0.145 kilograms. We already calculated this, but whoops, kg, forgot them, times negative 45.0 meters per second. Because it's got a negative velocity, it'll have a negative momentum, at least in this one-dimensional coordinate system. And I think it's the one I just figured out. It'll be minus 6.53 kilogram meters per second. Okay. Now the final momentum down here, P final, it's in the positive direction, so I'll have my 0.145 kilograms. Oh, and these are all MV, is what they are, 0.145 kilograms times 55 meters per second. And it's going to be different. It's going to be 7.98 with a plus sign kilogram meters per second. Now, the reason I wanted to get these is because I'm supposed to figure out the magnitude of the change in momentum of the ball. and of the impulse applied to it by the bat. Well, actually, those are both the same thing. The impulse, which we could use an I for, is going to equal the net force times delta t, and that will equal the change in momentum, delta p, which is going to be p final minus p initial. Okay, so that change in momentum, the final is 7.98 kilogram meters per second minus a negative 6.53 kilogram meters per second. Okay, so minus a negative means I'm ending up adding the two together. So 7.98, let's see. I get 14.5 for this. So delta P is going to be 14.5 kilogram meters per second. That's the change in momentum, but the impulse is equal to the change in momentum, so it's also equal to the impulse. And I is what we'll use for impulse. At least that's what I'm using. I'm hoping that's what the book uses. Every once in a while, they'll throw me a curve, I guess, and pick a different letter, but I'm hoping that's what they use anyway. Now, if the ball remains in contact with the bat for 2 milliseconds, which might not be that unusual, find the magnitude of the average force delivered by the bat. When you have collisions between things, like between a bat and a ball, if you make a graph of the force as a function of time, so this would be force versus time here, and the force may be 0 for a while, and then it'll kind of grow, and it might be something, maybe a bell-shaped curve. It doesn't have to be anything quite this tidy, but that would be the force as a function of time. Turns out on this thing, it's the area under this curve, which isn't really an area because it's newtons times time. It's not square meters or anything, but we still use that term, the area under the curve. That will equal the impulse. So under curve is impulse. Okay, well, when we were looking at work done, we talked about an area under a curve, but that was, in that case, we had force versus distance or position. Here we've got force versus time. Now, there's another way to kind of show this. We could calculate an average force if we had the means to calculate this area anyway, which probably takes calculus, but we could have the entire duration of the collision between the bat and the ball, or whatever it is we're considering, and this would be the delta t that shows up here, and the height of this thing could be the average force, and the average force times delta t is also equal to the impulse. So this area of rectangle which is F average, FAVG delta t, is also equal to the impulse. Okay. And so that's what they gave us here. We calculated how big the impulse was, and they tell us how long the collision lasts. And so we can also say that this impulse that we've got acting here is equal to the average force times the time of the collision. Now here I was just calling it F net delta T, which may not be quite correct when you're talking about a force that changes in time, but the average force times delta T is more of an approximation, and we can figure that out. So the average force is going to equal that 14.5 kilogram meters per second divided by the time of the collision, which is 2.00 ms. What's an ms? An ms is a millisecond, but m as a metric prefix means times 10 to the minus third seconds. And so down here I'll have 2.00 times 10 to the minus third seconds. And I'll get units of kilogram meter per second squared when I'm actually done here. Because if you think about a kilogram meter on top over a second and a second on the bottom, think of it second over 1, flip it and multiply, and you'll get kilogram meters per second squared, but that's a Newton. So this will tell us how many Newtons we've got. And I get a force of about 7250 kilogram meters per second squared, or 7250 newtons. Okay, and if I multiply that by 1 pound over 4.448 newtons, now this is a perfectly good way of expressing a force, newtons are, but we're not so familiar with newtons, but we are a little bit more familiar with pounds. So if I divide that or multiply by 1 pound over 4.448 newtons, I would get about 1,600 pounds, 1,630 pounds, which is a pretty good approximation. Well, not quite a ton, but it's a fair amount. I don't know if any of you have ever seen the high-speed photographs that people take of things. Oh, sometimes you'll see them of something like a bullet going through a water balloon or something like that. But I've seen them of a bat colliding with a ball, and it is amazing how much the baseball deforms when it's undergoes a collision like this, where you think of it as this round thing that's fairly solid, but it flattens out considerably when it's hit by a bat like that. And it's no wonder that in the major leagues, once a ball has been walloped in a hit, they don't use it again, because it's undergone some change anyway during that collision. So pretty amazing. So that's a large force. That would hurt, I guess. So anyway, let's not do anything with that, or where we have to expose ourselves to something like that. Okay, this is starting to look at conservation of momentum. We've had a little bit about an introduction to that stuff. I thought I had some more problems I ran off. Maybe it's over here. I did. Okay, here's another change in momentum problem. We have a rugby player who's initially running at 8 meters per second, which is pretty fast. That's like a sprint, but he collides head on with a padded goalpost. Still gonna hurt. he experiences a backward force of 1.76 times 10 to the fourth newtons. That's 17,600 newtons for 5.5 times 10 to the minus 2 seconds. So I can calculate the impulse here. That will equal the F average times the delta T, which is 1.76 times 10 to the fourth newtons times those seconds, 5.50 times 10 to the minus 2 seconds. And let's see what we get there. Okay, I will get 968. Now, this is a Newton times a second, but what we'll end up with is, we could call it Newton seconds, but I'm going to go a little farther with it. A Newton is a kilogram meter per second squared, and if I multiply it by seconds, I lose one of the seconds down here, and I'll have kilogram meters per second, which is good. Those are our units of momentum. And that will equal the change in momentum of this rugby player. Okay, well, that's going to be, we've got 968 kilogram meters per second is going to equal P final minus P initial, because that's what the impulse is equal to, is the change in momentum, or this is what the change in momentum is equal to, which is going to be the mass of the rugby player times V final minus the mass of the rugby player times V initial. So we've got this weird new thing we're calculating, things actually, impulse and momentum, which is probably about enough for one day once we maybe do another problem like this. Well, we're given the initial velocity. We can kind of draw a little picture for this. Here's our rugby field. Here's our rugby player running along here. And I don't know what makes him run into a goalpost, but he does. So I'm going to let positive be to the right here. And so that'll be that. And he's initially going 8 meters per second. Okay, so he'll have that. Clyde's head on with the goalpost. Does that mean he ran his head into it? I hope not. Anyway, he's initially got a positive thing there. Let's see. Oh, I need to put a sign on this, don't I? What should the sign be for that impulse? Impulse will have a sign. The key here is that I have to think about the direction of the force. He's running in this direction and he runs into the goalpost. Which direction will the goalpost exert a force on him? Or what will be the direction of the force that the goalpost exerts on this rugby player? It's going to be to the left. And so I should have a minus sign on my force here, which will give me a minus sign on my impulse here, which means this is going to be a minus sign. And so I can add this MVI to both sides, and I'll have the mass of the rugby player times V initial, which is going to be positive. I've got a minus sign on it here because I'm doing a subtraction, minus 968 kilogram meters per second. Well, let's calculate this. He's 110 kilograms. He's going at 8.00 meters per second. And I subtract from that 968 kilogram meters per second, and that will equal MV final. Well, let's figure out the subtraction here. 110 times 8 is 880. Turn on calculator first. And what I get here is actually minus 88 kilogram meters per second. Excuse me. And that will equal MV final. So when I just divide out by his mass, I'll get minus 88 kilogram meters per second divided by his mass is 110 kilograms. That'll be V final. And I get minus 0.8. I think I can only keep two significant figures here. Because of the way this subtraction worked out. I would have had 3 on this and 3 on this, but I'm down to just 2 there. So meters per second. And I did get a negative sign for that, which tells me that he bounces off the goalpost, but he's not going very fast when he comes off of it. So good thing it was padded, I guess. This collision is a lot longer. This would be about 27 times as long as the collision that the baseball had with the bat. And because of that, even though it's a pretty large net force, it'd be kind of spread out over the person's body. So still, that's going to hurt, I think. Poor guy. There's something I want to talk about with that F delta T business. And the I equaling F delta T. And this is something that points out the reason for padding on things. And that is, let's suppose that you're moving, or this could be you, but you have an object with a mass m that's moving with some v initial, and the object is going to be stopped. It's going to have a collision with something and be stopped. So let's imagine that maybe it's going to encounter some sort of a barrier here that's pretty much attached to the earth. And so they're not going to move this thing. Okay, so they're going to lose this object is going to lose its momentum. Now, if this thing is hard, just as hard as can be, like it's a 2-foot thick steel barrier, that would be pretty darn hard. When they collide with that, the delta T is going to be pretty short before they're brought to rest. And if this is short, it's like the baseball hitting the bat. When we divided the change in momentum by that little tiny delta T, 2 milliseconds, we ended up with a large force that acts on the baseball. It was almost a ton. Okay, human beings don't like having large forces as large as a ton hitting them, especially in just single parts of the body. The rugby player was bad enough, but we'll see what might happen in this case. But you can either have a large force, this is pseudo algebra here, and a small delta T for a small time, or you can have a larger delta T and a smaller force. This is the purpose of padding. on things like dashboards and stuff like that, and airbags in your car, what they do is they spread out the time during which your body is stopped from moving. So if you've got some amount of padding on this thing that you first contact and then you start compressing this padding on this steel barrier or whatever it is, while you're compressing that padding, time is passing and you're gradually being brought to rest. And so you've got a larger delta T and you can have a smaller force acting. You're going to stop no matter what. So you're going to experience the same impulse no matter what, but it can either be a large delta T and a small force or a small delta T and a large force. When I was a kid, the dashboard on the cars we had were steel. There was no padding on them whatsoever, and it was molded sheet metal. And we were just lucky we never experienced a collision where we would have smacked into that thing, because people got damaged in those collisions in those days. If you're not buckled into your car, when your car comes to rest in a collision, you become a projectile and you could run into an unpadded surface. But nowadays, most of the surfaces in the car are padded, plus you're belted in, hopefully, if you've got enough sense to wear your seatbelt and all that stuff. But and now modern cars have the airbags as well, things that inflate very quickly in a collision, and then you hit them and bounce off of those airbags, which are compressing while you're hitting them. And so they stretch out the time of the collision and minimize the force acting. Another way you can think of it is that, those giant inflated pillows that stuntmen fall onto when they shoot movie scenes where somebody's falling out of a building. The stuntmen who film those things land on these giant pillows, which they don't film as part of the movie. And it can actually take more than a second for one of those things to compress by its full amount, and it'll stop them before they actually hit the ground. And so they have a longer duration collision. And so you could actually have a very large time for the collision and a very small force. And that's the kind of collision that protects you from stuff. So there's something that happens in collisions. And it's just a different way of thinking of what can happen in those cases. Okay. We'll have a little bit of an introduction to collisions here. And we're going to come at this from a little bit of a different viewpoint. We're going to imagine that we've got some object here that we can call M1, and a second object that we can call M2, and they're moving toward each other. Now, there are all sorts of different viewpoints you can take with a situation like that. You could be traveling along with M1, in which case you'd think M1 is at rest and M2 is coming in with some speed. Or you could be traveling along with M2 and you'd think, okay, M2 is at rest and M1 is the thing that's coming in. Or you can adopt the viewpoint of what's sometimes called the center of mass coordinate system, where you see M1 and M2 moving. And we can just imagine, it doesn't matter which viewpoint we take, the momentum is going to be conserved no matter what we do. And I'll show you why it's conserved. So let's just imagine that M1 is coming in here at V1 initial, and I've got two subscripts on there this time. and M2 is coming in here at V2 initial. And so, whoops, how about V2 initial instead of an M2 initial, right? Now, here's something that's going to happen. When they start to come in contact with each other, M1 is going to exert a force on M2, and M2 is going to exert a force on M1. And let's look at the impulse that M1 receives from M2. So we will have delta P for M1 is going to equal the force of 2 on 1, and this would be the average force, times delta T, the time that the collision lasts. And that will equal the change in momentum of mass M1. At the same time that's going on, we will have M2 undergoing a change in momentum, delta P for M2, and that will equal the force that mass 1 exerts on mass 2 there, times delta T. And these delta T's are equal because if they're starting to contact each other, they're both going to be experiencing that at the same time. And here's something else. The force of 2 on 1 is the negative of the force of 1 on 2. What? They're equal to each other and opposite. These are third law partner forces. Well, that's kind of interesting. Here's something else. If I add these two things together, delta P M1, delta P M2, this one's equal to the force of 2 on 1, delta T. This one's equal to the force of 1 on 2, delta T. They're going to be equal in magnitude and opposite in sign. When I add them together, I'm going to get 0 on the right side of the equation. What I'll get on the left side of the equation is delta P M1 plus delta P M2, whoops, that's supposed to be a subscript, is equal to 0. That tells me that when you have a collision between two objects, the change in momentum of the system is going to be 0 if you consider the two objects the system. Another way you can think of this is the change in PM1 plus PM2 is equal to 0. That's the change in the total momentum of the system. PM1 plus PM2 is the total momentum of the system. And you can write this all sorts of different ways, but you could say M1 V1 initial plus M2 V2 initial. Whoops, I got this in the wrong order. Yeah, let me start that over again. This delta means M1 V1 initial, whoops, V2 M1 V1 final plus M2 V2 final is going to, whoops, minus, there we go, M1 V1 initial plus M2 V2 initial. That'll equal 0. Okay, here's my final momentum. Here's my initial momentum. I could juggle around with things on here, but in a collision between two objects, momentum is conserved. And that's something that we'll start investigating tomorrow. And this is true in any collision. And here's the way that you can state it more formally. I'm going to say, in the absence of external forces or before they can act, the momentum of a system remains constant. Okay, so if we've got these two objects running into each other, before the external forces can do any work on them, do anything to change things, they'll have the same amount of momentum after the collision that they have before the collision. And so immediately after the collision, they'll be going in some direction that's determined by their initial momenta, and you'll be able to set up some kind of an equation like this. Now, eventually, those external forces, like say it's two cars that smack into each other and they're getting dragged along the ground, eventually the external forces of friction are going to bring them to rest. But immediately after the collision, they'll be going any direction and with a combined momentum that's determined by what they had to begin with. And people like State Patrol accident investigators look at the length of the skid marks. From that, they can go back to right after the collision and they can figure out how fast the two cars were going that ran into each other. And so that's accident reconstruction. And they're basically using conservation of momentum most of the time on those things. Energy would not be conserved in a collision like that. Anytime you can hear a collision, energy was not conserved because it takes energy to make sound, and it also takes energy to deform metal permanently. And so that's not going to be conserved, but momentum is always conserved. So that's a neat thing about conservation of momentum, that it doesn't matter if a collision has energy saved or not, the momentum will always be saved or conserved, at least until those external forces can do work on things. And we'll move on with this tomorrow. But today, we got an introduction to what momentum is, mass times velocity, and then impulse as well. Impulse is a force times the amount of time that that force acts for. So 2 new ideas today. And I've got stuff to post and stuff to send out and still all kinds of things. But hope to be doing that soon, to send out the test 1, no, test 2 redos. That's the one. I got test 1 mailed out. It's test 2 I still have to do. So,
do you know when the last lab is due?
I put a date on it, but I forget what it is. Let's see. Not off the top of my head. I think it's either late this week or early next week. I could look, actually. I can go to, let's see. Go to the right class. 114. Coming up, nothing for this week. So I must have done it for next week. Labs. Let's see. Finding G with a pendulum. June 14th. Next Monday is when it'll be due. So got a little bit of time on it, but you may take a week at it, or take a look at it early this week and see if you have any questions on it. Find anything I forgot to give you for it. So yeah, have a look at that. But otherwise, you've got a week on that thing. And I hope by not too long that I'll have that. Shouldn't take me too long. I think I've got it set up fairly efficient, but I'll have your test 2 retakes graded, so I'll bounce those back to you. Okay, I'll stop and see you tomorrow.